All right, welcome back. Today, we're diving into an absolute classic of chemical engineering design, the McCabe Thiele method. Now, this isn't just some old school technique. It's a really powerful graphical tool that lets you see how thermodynamics and mass transfer work together so you can figure out the perfect design for a distillation column.
So here's what we're going to cover. First, we'll set up the challenge. Then we'll get into the language of equilibrium, the basic rules. After that, we'll build the diagram itself piece by piece. We'll solve a real problem with it. And finally, we'll talk about where this method still fits in today's world.
Okay, so let's say you've got a mix of benzene and toluene. How are you going to separate them into really pure products? I mean, we all know distillation is the way to go, but the real engineering questions are, right, how many stages do you need to hit your purity targets? And where's the best spot to put the feed? That's exactly what the McCabe Thiele method gives us a visual way to solve. Okay, let's get into it. Before we can start drawing anything, we've got to lock down the principles behind it all, the thermodynamics and the mass balances that make this diagram work. Think of these as the rules of the game.
So everything, and I mean everything in this method hinges on one core concept, vapor-liquid equilibrium, or VLE. That VLE curve you see on the diagram, that's the thermodynamic limit for a single stage. It's telling you the absolute best enrichment you can get in the vapor phase. And that gap, the space between the VLE curve and that simple x equals y line, that is the fundamental driving force for the entire separation. The bigger the gap, the more separation you get per stage.
And what gives that VLE curve its shape? Well, that's where relative volatility, or alpha, comes in. Alpha is the number that really controls the size of that gap we just talked about. It's the key parameter that tells you, just by looking at the graph, how easy or how painfully difficult this separation is going to be. This table really breaks it down for us. If alpha is exactly 1, your VLE curve is just sitting right on top of that x equals y line. What does that mean? No separation. It's impossible. You've got an azeotrope. But as alpha gets bigger than 1, that curve starts to bow out, creating that all-important gap. The bigger the alpha, the more it bows out, and the bigger each of those graphical steps, which we'll get to in a minute, is going to be. And that means you'll need fewer stages to get the job done. Okay, now for a really key simplification that makes this whole graphical method possible. It's called constant molar overflow, or CMO. What we're doing here is making a pretty reasonable assumption that the latent heats of our two components are about the same. If that's true, then for every mole of vapor that condenses on a tray, another mole of liquid is vaporized. And why does this matter? Well, it means the liquid and vapor flow rates stay constant in each section of the column. And that is the magic that lets us draw our mass balances as simple, straight lines. Without CMO, this whole thing would be a mess of curves.
All right, let's get to the main event, building the diagram itself. Think of this as our engineering workbench, where we're going to take all those principles and numbers and turn them into a visual model of our distillation column. Building this thing is a really systematic process. We're just going to follow these 5 steps. We'll draw our oxys and the x equals y line, plot that VLE curve, put in our compositions and the Q line, figure out our reflux ratio, and finally, draw our operating lines. By the end, we'll have a complete model of the column on one graph.
So here's the problem we're going to solve. We're separating benzene and toluene. Our feed is 40% benzene. We want our distillate, the product from the top, to be 95% pure benzene, and the bottoms to be only 5% benzene. The system has a relative volatility of 2.5, and our feed is coming in as a saturated liquid. Those are our specs.
That last piece of info, the feed condition, is super important because it determines the slope of what we call the Q line. Since our feed is a saturated liquid, it means its Q value is exactly 1. Think about it, it's not a vapor, so it's not going to flash and create more vapor when it enters the column. It just joins the liquid flowing down. Now, if you look at the math for the slope of the Q line, which is Q over Q minus 1, well, if Q is 1, you're dividing by 0. That gives you an infinite slope, which means our Q line is just a straight vertical line right at our feed composition. Now, this equation here, this is our rectifying operating line. It's basically just a mass balance for the top part of the column, the part above the feed. And what's really important to see here is that its slope is controlled by R, the reflux ratio. That's our main control knob as engineers. We decide how much liquid to send back down the column, and that decision directly sets the slope of this line. Okay, our workbench is all set. We have all the lines, all the curves we need. Now it's time to actually use it and solve this thing. Let's find our answer. First things first, we need to decide on our operating reflux ratio. And we can't just pick a number out of thin air. We start by finding the absolute theoretical minimum, what we call R min. At that point, you need an infinite number of stages, which is obviously not practical. Then we use a common rule of thumb, an economic heuristic, to find our actual operating point. This is all about finding the sweet spot, right? The trade-off between buying a taller, more expensive column, that's CapEx, and paying for the energy to run the reboiler forever, that's OpEx.
So how do we find that R min? Graphically, it's pretty neat. You just draw a straight line from your distillate composition point right through that critical spot where the Q line and the VLE curve cross. The slope of that line gives you the minimum reflux ratio. For our problem, that comes out to 1.44. And if you look at the diagram, you can see that at this R min, the operating line literally pinches the equilibrium curve. There's no driving force left at that point, which is why you'd need infinite stages. It's our theoretical limit, but it's not a real-world operating point.
Okay, so now we use that rule of thumb. A pretty standard one is to set your actual operating reflux to about 1.5 times the minimum. So we do the math, and that gives us our R of 2.17. What does this do on the graph? It lifts our operating line up, away from that pinch point. Now we have a real, finite driving force for separation at every point in the column, and that's going to give us a practical, finite number of stages.
And now for the coolest part of the whole method, stepping off the stages. We're literally going to draw a staircase down the diagram, and each complete step represents one theoretical stage. The horizontal line over to the VLE curve, that's the equilibrium flash on the tray. The vertical line down to the operating line, that's the mass balance. It's the vapor from that tray mixing with the liquid coming down from the tray above. It's amazing, really. We're graphically solving the mass and energy balances one stage at a time just by drawing a staircase.
So we just keep drawing these steps all the way down. When our staircase crosses the Q line, that's our cue to switch from the top operating line to the bottom one, the stripping line. We keep stepping down until we finally passed our target bottoms composition of 5% benzene. Then we stop and we just count the steps. And for this problem, the answer is 12. We need 12 theoretical stages to make this separation work.
But wait, there's more. The diagram doesn't just tell us how many stages we need, it tells us where to put the feed. Remember when we switched operating lines? That happened on the 6th step. That's our optimal feed stage. And why? Because that's the stage where the liquid composition inside the column is the closest match to our feed composition. If you put the feed in there, you get the least amount of thermodynamic disruption and the most efficient column. It's just elegant.
And of course, we can run the numbers to double-check our graphical work. This table here shows a precise stage-by-stage calculation. And what do you know? It backs us up perfectly. You can see the liquid composition drops below our feed concentration right at stage 6, and the bottom's purity finally gets below our 5% target after the 12th stage, which, remember, includes the reboiler as the final stage. The picture and the numbers agree.
So there you have it. We have our design. But this raises a big question, right? This method is almost 100 years old. In an age where we have incredibly powerful computer simulators, where does a hand-drawn graph still fit in? Well, here's the crucial difference. The McCabe Thiele method builds your intuition like nothing else can. You can physically see how changing the reflux ratio changes the slope of the lines, and how that directly affects the number of stages you need. Now, modern simulators, they're amazing. They give you incredible precision, they can handle dozens of components at once, but they can also feel like a black box. They spit out an answer, but you don't always see the why behind it. And that's really the best way to look at it. They're not competing tools, they're complementary. The graphical method gives you that fundamental insight, that gut feeling for how the system works. It gives you the context you need to look at the number from a complex simulation and say, yeah, that makes sense, or wait a minute, something's not right here. One tool builds your understanding, the other delivers the final precision. And that really gets to the heart of why this method endures. It's never been just about getting the right number of stages. It's about developing a deep, intuitive feel for that dance between thermodynamics and mass transfer. It's about knowing why the answer is the answer. And that leads to a final question. When is an engineer's intuition, built with a simple tool like this, even more powerful than a complex calculation? That kind of understanding, well, that's a tool that never goes out of style.